Again, going back to the combinational logic chapter, let's spend a bit of time looking at other ways that we can use Verilog statements to create powerful and complex things. Demultiplexers are simply the opposite of a multiplexer, and notice the simplicity with which we can synthesize this, simply a left shift. We'll talk about that a bit more. In fact, let's go ahead and move on to decoders, where we can think about that in a little bit of detail. What is a decoder? It's a rather simple device. We're taking an n-bit binary input and turning one of the outputs on. So, for example, if our input is 3, then we turn output 3 on, whereas outputs 0, 1, and 2 would be off. Notice the approach we take. We've seen that in the previous section with demultiplexers. It comes into focus perhaps even more clearly in this section. For example, if our input says I want output 2 to be on, then we simply take the bit 1, shift it twice, so of course that's going to produce a value which we'll talk about here. So again, we've got a, let's say, 4-bit output, and we start with the number 1 in binary, and when we say shift it twice, here's one shift, here's our second shift, and if we simply number our bits, right, we always number our bits starting at 0, so this would be bit 3, 2, 1, and 0. So by shifting it twice, we've caused output 2 to be a 1, whereas all the other outputs are at a 0. So you can see the shift operator in action is a very simple Verilog method to go about and create a decoder. If you'd like some more information on how exactly a logical shift works, there's a nice article on Wikipedia, some good diagrams which will help make that a bit clearer. Let's take a look at the first exercise. Again, let me encourage you to solve these exercises on your own. These exercises are often just a few lines of code, if not a single line of code. They're designed to help you learn the language. If you use an LLM, if you're using Google to solve these, then you're missing out on a fantastic learning opportunity. And primarily, this exercise just points out an application for a decoder, because the problem itself is create a 3 to 8-bit decoder. In our previous example, notice that we had a 2 to 4 decoder. This means that we take 2 bits of input and produce 4 bits of output. In the first exercise, notice that we're taking 3 bits of input and producing 8 bits of output, hence the name 3 to 8 decoder. All this example is exactly that. It is a 3 to 8-bit decoder, and the decoder can be used for the example given here, which is lighting up 8 different LEDs to represent the floor at which an elevator currently resides. There are many other applications, but this problem is simply implement a 3 to 8 decoder, nothing more than that. In our next exercise, we add just a little bit more complexity. What if we wanted the ability to optionally turn some of our bits on? Again, going back to our example, when we have our input, let's call it n equal to 2, then we're turning the bit 2 right here on. If we have our enable, even when n is 2, we'd like to turn everything off when it's disabled and turn just one of those bits on when it's enabled. And again, this is very easy to do by simply adding the conditional operator. We've already seen that, but it's worth looking at again. We can simply, again, remind yourself how the conditional operator works. If the enable value is true, they would put R1 shifted by n value. If the enable value is false, then we would bring a 0 through, and that would define everything we need for a decoder with an enable input. An encoder is just the opposite of a decoder. It's taking 2 to the n inputs and producing an n-bit output. In terms of our example here, it means if we had something like this, then this would be our input. This 4-bit value would be our input, and as output, we would like the device to tell us, or the module to tell us. In this case, n is equal to 2. It brings up a couple interesting questions. One is, what should we do when we have something that doesn't follow our pattern? For example, what if we had an output like this, where instead of having just 1 bit on, we have 2 bits on? What should we produce as our output in this case? This is where we can assign a default value or provide an initial value. In this example, you'll see that I've taken the default value approach. In other words, with the case statement, there is a default option saying, what should we do if none of the previous cases, in case, bit 0, bit 1, bit 2, or bit 3 are on, if none of the bits are on or multiple bits are on, we can use this default statement. This is an alternative to simply assigning a statement at or assigning a value to out at the beginning of the case statement. And interestingly, by saying it's X, that's a don't care or an unknown value. That allows the synthesis engine, when it's producing the circuit, to pick whatever value it can that would minimize the resulting logic. So it's a nice option to give the optimizer and synthesis engine freedom without over specifying design, because we really don't care in this case what output we would get. So this is just an alternative way to accomplish the same thing, which is, but here's the important part. Remember, we always want to avoid inferring a latch. We always want to define the value of output no matter what value input, in this case the value n we have. And this is an alternative method of accomplishing that goal. Encoders are powerful. Case statements provide us a simplified and straightforward way to accomplish the creation of an encoder. They can also be used for muxes. You've seen the shift operator works for both decoders and demuxes or demultiplexers, because both encoders and muxes, decoders and demuxes, are very related things. Here again, in our first exercise, is simply a straightforward encoder. Use the standard case statement output. You can go ahead and define the output value. Of course, it's called out as 111 at the beginning of the case statement, or you could use the default statement, and then simply provide the appropriate series of cases that would allow us to determine the final value. In the second example, this is something that is, again, very much tied to a real-world physical product. I picked the Grayhill Series 88 keypads. The full spec sheet of the keypads provides a lot of information. Notice the way that these keypads work. There are 2 different configurations that the company offers. One is where you have lots and lots of conductors, A through N. Another is where you have a much reduced set of conductors, and the switches are arranged in a matrix configuration. That's the one we're going to make use of because it does minimize the number of wires, even though it produces the need for a little bit more logic. So the basic idea is, what we'll do is we'll turn on one of the rows. Now, in our design, we're going to call this row 0, row 1, 2, and 3. We're always going to count from 0. We would put the value 1, a plus 5 volts, in row 0, and we would put zeros on all the other rows. This guarantees that all these rows have a defined voltage applied to them, and of course we do that quite simply using a decoder. Once we've established those voltages, switches connect a row to a column. So for example, if we press the 1 button, if we press this button, what it's going to do is connect the row 0 input to the column 0 output, which would mean column 0 would be a 1, columns 2 and 3 would remain at a 0, assuming that we provide the appropriate pull-down resistors. That would be an external part of the circuit that we use to connect to this keypad and not something that we need to worry about from a Verilog perspective. So we would get a 1, 0, 0 output from our 3 columns when button 1 is pressed. Similar principles apply to the other rows. This switch matrix confirms that intuition, saying when we press the button 1, letter F and letter J, and if you go back to the data sheet, you'll see quite clearly which terminals are connected together. From a high-level perspective, a controller would say, check row 0. Our module would send the decoded row value, that 1000 value, look at the result from our keypad, and then return the value from it. We're using a concatenation. Let's take the row value and the column decoded value and make a single number out of it. For example, the value 00001 is exactly what we talked about, where that would imply the 00 means we've selected row 1 to be on, or sorry, row 0. And then the 0100 comes from the 100 result of column 1, indicating that we've pressed keypad button 1. Notice again that Verilog allows us to simply glue these 2 bits of row to the 3 bits of column to produce a 5-bit value. I've inserted an underscore in the resulting value. That makes it easier to read, but of course it doesn't affect the number at all. And System Verilog allows us to do this because it's rather common to refer to various bits that are grouped together and make larger bit fields. We can simply put a case statement in and then walk through each of these individual cases to decode all 12 numbers. Notice that if no button is pressed, multiple buttons are pressed, we'll just return the value 1111. In our next lecture, let's spend a little bit of time starting to think about more complex ways of handling Verilog code. We talked about this just a moment ago in our use of encoders, but let's look more fixedly at local variables and concatenation.